This kludge I built some time ago when we were building a linear translator in the San Francisco Bay Area many years ago, similar to what the Oscar satellites were doing at the time, Oscar 10 and 13, which takes one band and converts to another band so that people can have access to multiple modes and so forth. Anyway, this was for sweeping the IF. It's an actual VFO from a multi-2700. And over here on the side we have some circuitry that is a power supply and double balanced mixer. And in the back you see a 1 kilohertz tone generator, which is used to make double sideband by putting a tone into the double balanced mixer. So let's take a look at what that actually does for us, and we can see how the two-tone generator looks on the spectrum analyzer as well. Here we have the analyzer set up. I just turned it on, so it's just got the 0 to 1500 megahertz. I'll turn on the power supply for the generator here, and as you see down at the low frequency here, you'll see the modulated signal from the double balanced mixer. It's actually 10 megahertz, 10.7, which is where the IF was for the translator. Alright, so let's do two things. First, let's change our frequency to a start frequency. The start's okay, but stop frequency of maybe 100 megahertz. So now we're seeing everything from 0 to 100 megahertz. This being the IF frequency of about 10.7. Let's see what the peak detector thinks that is. It says it's 11, so that's pretty close to 10.7. And we have other peaks here going out from it as well. It is just a double balanced mixer. There's no selectivity at this point. So I've got the peak here. Now let's move the marker to the center frequency. Now the marker's in the center frequency, and you can see that I'm not exactly on the peak, so that's why it's at 11 megahertz. But it's close enough for getting the thing into where we want it to be. I'll hit the span here, and we don't want to be at 0 span. We do want to zoom in, but let's just make it, I don't know, maybe 200 kilohertz. And we've lost our signal now. So it was, let's see here, span frequency 11 megahertz. Let's make that 10.7. There we go. Now we're back in business. All right. So now let's make the span maybe 20 kilohertz. Okay. So we have a 20 kilohertz span. We have a frequency that's slightly higher than 10.7, obviously. So I'll tune the unit down to 10.7 in the center frequency here. The marker is at 10.71. So let's put the marker at 10.7 megahertz. There it is, right in the center. Okay. So that's the suppressed carrier down there. This is 1 kilohertz up and 1 kilohertz down from that. This is distortion based on the carrier here, and then this is the third order product of the double sideband, and so forth, fifth and seventh and so forth. This is with 300 hertz receive bandwidth. Let's go to a bandwidth of, rather than 300, let's go to 100 hertz. Now we can see all the peaks and valleys of this thing. pretty well. So there's the occupied bandwidth of this unit for testing purposes. The output right now is a little on the high side. Should be about -20 per peak. So let me drop that down here. Alright, that's about where it should be. And at -20 dBm per peak, our distortion products are about 30 dB or better down, worst case, which is what I expect. That's about what we are able to do with the particular balanced mixer we used here, which is a mini circuit, just a run-of-the-mill plus 7 dBm input type double balanced mixer. But still, that's 30 dB below the average power, which each peak represents the average power. The peak power, of course, is 6 dB higher than this, and so we're 36 dB below below PEP here. That's the relationship. And if you want to see the peak power, what we do is take the bandwidth here and go up to, say, 3 kilohertz. We'll take both of these in, so 3 kilohertz. And now you see that the peak power is higher. Probably even a little higher than that, but anyway, you get the general drift of the situation here. And we'll go back to receive bandwidth of 100 hertz. So, there you go on 10.7 megahertz, an IF frequency for a linear translator, and I would expect whatever IF that I was testing would have this same general level of distortion when I put this signal into it. And the idea is to set the AGC so that we don't exceed this. Let me do one more thing. I'll drop the level even more here. Notice how the center stays about the same level, because that's the level that comes out of a double balanced mixer. But let's say I wanted an AM signal for testing. I could have an AM signal based on the levels that I now have here, with both sidebands about 6 dB down below the carrier. So there's an AM signal with pretty good rejection of distortion products, but of course it's much lower in level. I haven't unbalanced the balanced mixer to generate more of a carrier, and don't actually have any means of doing that in this instance. Let me bring this up a little bit by going to an amplitude input attenuation. Since I've got no problem with overload here, we'll go to 0 dB on that. So that brings it out of the noise more, and you can see that the noise is well below the 30 dB level. And in fact, let's do this. Let's go to reference level of -30. Okay, I don't have enough signal here to get above the noise level, so we can't check it any further down, except possibly if I can't go below 100 hertz either. So there you go. That's just what it is right there. Now what I can do, however, is I can go to the bandwidth here, and the video bandwidth I can go down to 10 hertz, I believe. So there you go, very clean AM signal, needless to say. That's looks like it's got about 30, well, from the carrier there, it's got about 38 maybe dB. Let's look at the peak again. There's the peak, and let's look at the marker and do a delta here and find out what the so it's 39.91 it says to the noise level, with no distortion products aside from the two sidebands. So it's a pretty good AM signal, and if you were doing something with AM, this would be a good signal to use. I've set this up again to display the double sideband signal. What I've done here is I've set the amplitude this is these are each minus 26 dBm. This is minus 20, but I've set it up so the reference says 0 because I want to see the dB below each below PEP here, and what I've done is I've used a reference offset here of 20 dB to do that. If I put this back to 0 dB, you'll see that it stays the same, except this is now minus 20 dBm at the top, whereas if I put 20 back in here, it references to a reference of 0 dB, not really dBm, but dB. And our center frequency here is the marker, which is at 10.7 0000, and that happens to be 38 dB below PEP. And if I want to know what the rest of these, I could of course scooch around here and find out. Like put this here, tells me that my actual frequency is actually 1.1 kilohertz apparently, that's driving this double sideband double balanced mixer, because I'm at 701100, so that's what that oscillator's actual frequency apparently is. And if I want to find the rest of these, I can do it manually, or I can just hit the peak here, go to the second screen, and set up a peak table by turning that on. It gives me the frequencies of each one of those peaks and the third order intermod. You notice that we have about minus 50 on the display line here, and also we have a peak that's just below that, but I've also adjusted the peak table search parameters here so that it's searching for peaks that are 2 dB above a peak threshold level of minus 50 dBm or minus 50 dB. So it'd have to be at minus 47. This is remaining below minus 47. Thus, it's not showing up as a peak, but neither are any of these noise elements here. So anyway, that's how I got to that screen. And we'll go back to peak, and we'll go back to the peak table, and then you see that we have minus 41 on number 1 here, minus 6.28 on number 2, number 3, which is the carrier, is minus 38 approximately, 6.28 on the number 4 here, which is the other double sideband carrier or modulation, and then minus 41 or so on this guy. This one happened to go up high enough to see for once, but it's around minus 50. And on this side, we don't have much in the way of the fifth order product. Occasionally it comes up to minus 54 or something like that. So that's the cleanliness, if you wish, of the spectrum of that particular double sideband generator when we have each tone at minus 26 dBm or 6 dB below PEP, which is of course minus 20 dBm. Someone sent me an email or possibly commented on my site, I don't remember, but about AM broadcast signals and occupied bandwidth. So I'm going to take a look at that. I've started out here by looking across the entire spectrum of 0 to 1500 megahertz to see if there's any big signals that are too big to deal with. I don't see any, so I think we're okay to set the frequency here to start at 500 kilohertz and stop at 1800 kilohertz. There's a composite of the entire AM band in the San Francisco Bay Area. That's because our receive bandwidth here is 30 kilohertz wide, or 300 kilohertz wide. So let's go to something more rational, like 3 kilohertz for AM stations. There we go. That's a little better. All right, so we have a couple of fairly good-sized signals here, and I'll ignore the rest for the moment because I want to show you the occupied bandwidth. This one is a local one, 1590. KLIV is a news talk radio. And so I'll go frequency, center frequency, 1590 kilohertz. Put it in the center. All right. Then I'll go to a span of 50 kilohertz to look at its occupied bandwidth. But of course at 3 kilohertz receive bandwidth, that's not going to work too well. So we will drop this down to the minimum, which is 100 hertz. And now we see the modulation as it occurs here. Not quite real time at 100 hertz. Let's show you what it would be at 300 hertz. 300 hertz. So a little bit better there. But remember, this analyzer has one feature that's very nice, and that's I can go to a second trace here, which is number 2. It's blank now. We'll go to max hold on that one. And it's going to build up the modulation mask for this thing as things go on. So there's your modulation mask for 1590. And I'm going to also set the reference up to here. So it looks like about 23 dB down at this point. And so I'm going to put the, go to amplitude here and the reference level and go to 23 minus dBm. Okay, that looks about right. And then to make this a 0 reference instead, I'll just use a reference offset here. We'll offset it by 23 dB. 23 dB. And there we go. So now we have a 0 reference here, and any sidebands can be measured directly down to, looks like about 60 dB here. So that's a standard AM station with nothing special going on. There might be, let's see, this is 5, 10, 15, 20. That might be another signal from outside the area. I don't know, but there is this sideband. It might be a sideband too, because it's equal here and not quite on the 20 kilohertz marker. So anyway, so there's a standard AM signal. Now let's turn this trace off again. Trace type will blank that trace, and we will change the frequency here to 1170 kilohertz. And you notice right away that there's a difference between this and the last station. 1170 is KFAX, and it's I believe in Oakland, I don't recall. But anyway, it seems to have more going on than just standard AM modulation. Let's also put our trace back on here. The reason I'm doing this, by the way, is so that we get rid of the old stored max trace or max hold information. Now you see how this one is 5, 10, 15 kilohertz down and up. and you see a plateau here and a plateau here. This is HD, I'm fairly certain. And I went on their site and they do broadcast AM HD radio. So there's a subcarrier HD channel here, probably music, and it might even be a video. It can handle that apparently. But anyway, that's what it looks like. So I thought I'd give you both of these and how easy it is to set this up for doing this kind of work. And it does the job quite well.